Good morning, everyone. Thanks to Ted and Sam for setting this whole thing up and for inviting me to speak. And thanks so much to James for a very inspiring presentation. I'm going to take things in a slightly different direction. My name is McCormick. I'm a Canadian composer and performer, and moved to Norway, or moved to Scandinavia about 10 years ago, where I've been living until then, or since then. And I've also been working with supercollider since that time. So that was just had a crisis that year or something. I use supercollider for a lot of different projects as a composer, sound designer, or whatever. But this morning I'm going to talk about a project that's maybe a little bit of an alternative or non-conventional use of supercollider, which is the instrumental metal band YAWN. There's 3 of us in this band, which is based in Oslo. 2 8-string guitars and a drum kit. And we have sort of, since the beginning, tried to keep everything in-house in terms of production, sound design, recording, mixing, light programming, etc. Nice, thanks. So I thought we would just start with an illustration of sort of what all this looks like, and then I'll sort of break down how we approach this. This is an excerpt from a song of ours called Tokamak from a concert in 2022. I should warn you, there's some flashing lights. If you're sensitive, you can sort of hang out until the music stops. And hopefully it's not too loud. Let's see. Hopefully. Yeah, thanks. So yeah, we'll just take a look at the hardware setup first. We've got, as I said, 2 8-string guitars on stage using Kemper digital amplifiers. Look at it. Should I? Whoops. Oh, I'm never going to be able to close that window up there. But anyways, there's a computer with supercollider and then a drum kit. The analog outputs from the guitar amps go to a mix rack on stage, along with the microphone signals from the drum kit. Those are connected to front of house with a Dante network over Ethernet. And my computer is also connected to the mix rack, taking both the signals from the analog inputs and then also sending to front of house. I've got a MIDI cable coming from my computer going sort of daisy chain to the amplifiers, and then a USB to DMX interface, which goes to a floor rig that we travel with, very like simple rig for smaller venues that maybe don't have the kind of lights we like. But then we attach into the house system. And everything is controlled wirelessly by a tablet at the drum kit, and I have a tablet by my amplifier as well. Yes, Super Collider. So everything in this setup kind of developed as we went from sort of musical needs. So we were writing songs and they're like, how are we going to do this? So the first, one of the first songs we were working on had a riff where every second bar was in a different tempo. And we were trying to learn all these metric modulations, and I suggested, like, let's just make a click. I could do it very quickly. So I made this click class, which sort of a very simple metronome. All of these are pattern wrappers, essentially. So in the first click, we have at the tempo 120 BPM, 4 beats with sort of 8-note or 2-beat subdivision, repeating twice. Beautiful. Exactly how I expected it to be. And then I think also in the process of working on this song, we had a riff with a lot of repetitions. And somebody in the band suggested that, okay, is there some way that we could use this click to let us know when it's like the last repetition to move on to the next section of the song? So this click cue class, it's hard to say, plays back a sample on the downbeats of the click. Otherwise, it's the same. Bell's very nice. It usually cuts through the mix. Sounds out of place. Then we started, we had a song with a long unison retardando at the end. It was very sort of dramatic, and we wanted to be able to play it tight and in time. So I made a class to ramp between 2 tempos. This one has also triplet subdivisions, which sort of helps to feel where the next beat is coming. So this is ramping from 75 to 120 BPM over 4 beats, and then repeating twice. And then I made, I think, naming things is hard. I think I chose man for manual. Click manual, click man lets me put in the tempos, the BPMs for each individual beat in a bar. So this is taken from a drum solo we have in one of our songs that is sort of 11 beats, felt as, 4/3/4 or long, short, long. And then I made improvisation is a big part of our live performance, both sort of free, expansive, ambient, noisy improvisation, and also sort of cyclical improvisation, more like in a jazz context. So I wanted to be able to loop clicks, and then this uses p-while internally, and I can set a flag via that loop key to sort of exit the loop. I don't need to play that for you. You can imagine what it sounds like. Click concat just concatenates a long string of clicks and allows us to repeat it for, say, a section that's repeating, and then another class to loop those long concatenated clicks. Yes, so that was sort of the starting point. And then the other guitar player wanted to get into programming lights. We had to sort of figure out a way to connect all that into this grid. So I made a class using Christoph's VST plugin This, because we're using this, until now, we've been using this DMX's very sort of simple DMX, USB to DMX converter. It has a very old interface, and this plugin has one universe. You can make presets and move all those faders up and down to control the channels. The way we work is that our guitar player who likes to work with light programming will make MIDI programs to sort out all the lights, and then exports a MIDI file, which comes to me. And this YAWN DMX's class loads the MIDI files based on song, and then also the section of the song. I'll explain this a little bit later, but basically we separate our songs into different sections for rehearsals and things like this. And this is also another pattern wrapper. So this takes MIDI files and then sort of translates it into a pattern. Likewise with the Kemper, these are the digital amplifiers, the Kempers. So they also come from a program MIDI file that can do preset changes. So we can change from a very heavy distorted guitar to a clean lead guitar, and also automation. In the video that we heard, there were like these ring modulation things that were happening on the guitars. So that's all MIDI files turned into patterns. YAWN PB is playback. So these are for our backing tracks. These also get a bus key because on our front of house mixer, we send different backing tracks to different channels. So the engineer can, mix the percussive sounds differently from the synth pads and things like that. All these classes get used to build a song. This is one of our sort of more straightforward songs. It's an array of events, which kind of like a JSON file. I guess here's a close-up of one of those sections. So each section of the song has a name, and then a bunch of classes to, essentially, these all turn into patterns and get loaded into a PPAR eventually, or several PPARs. Part of the reason we separate things in these different sections is, like I said, to be able to, in rehearsal, not always have to go back to the beginning of a piece, but also we've been experimenting with building sets where we play the first half of a song and then go into something else and then bring it back later, and sort of breaking the songs apart and playing them over the course of an entire set. So this dictionary, this library of all the patterns belongs to a YAWN song class. And to initialize the show, I pass a couple of dictionaries with input and output routing to a YAWN show class, which then sort of routes all the patterns to the right places, sort of connects to the MIDI devices, and then also loads our tablet interfaces. Yeah. Right. So these are some of the things that we've been using the system to do that I would say maybe fall a little bit outside of the traditional metal genre, and maybe are a little bit less easy to accomplish with traditional performance tools, DAWs and timeline software, things like that. So as I said, we do some improvisation. This is sort of a screenshot of my tablet interface on stage. So I have the set list on top, and then on the right-hand side, the right column, there's different cues in the song for starting different sections. And then in the middle, there's some, processing controllers. This is also all done in supercollider. Here's an example from a recording we released in 2022. It's sort of a drum solo with some sugar on it. etc., etc. Something we've been experimenting with lately is polytempo. I know Derek's going to talk more about polytempo later this week. Exciting. This is a song that will be coming out hopefully this year as a single. So what's happening here is the drum kit is, these are sort of a graph of our tempos here. And you can see these nodes are some places where we line up. The lead guitar is just playing 4/4 at a steady tempo. The drum kit slows down and then speeds up, and the rhythm guitar speeds up and slows down. And after 4 bars of 4 for each of us, it all lines up. Possibly. Is it a device setting? Right. Up here, yeah. Yeah, that maybe. You can do it without high fidelity. Yes. Another thing that we've been experimenting with, but haven't sort of performed live yet, is what I'm calling generative riffs. So the click cue class that I mentioned earlier can play sort of any arbitrary buffer along with the click. So I made a bunch of samples of like a text-to-speech thing, just reading off, I think the numbers 1 to 4 in 2 voices, sort of a Anna and Dan. And then we made a set of rules. Well, first we can hear what the click sounds like anyway. So
2, 3, 3,
1,
2,
3.
So the idea is that we hear 2, and then there's 2 more beats in the bar, and then the next cue comes, and maybe it's 3, and then there's 3 more beats. So the sort of rule we thought was like, okay, we'll wait that many beats that we hear, and then if it's Anna's voice, we'll play the last 2 16th notes, and if it's Dan's voice, we'll play the 2 16th notes on that beat, on the last beat of that bar. Sort of improvise the pitches, and then there's sort of a B section where instead of playing these 60-note things, we're playing just low notes on the 8-string guitar. Let me see.
2,
Just gonna
3, 3,
I don't know how
1,
to skip
2,
the click without blowing lights up.
3.
This is a demo, by the way. So
3.
it's, the drums are programmed, and we haven't decided yet if this will even be possible to play live. It's interesting to think about sort of how this could turn into an interesting performative setting where maybe the song has the same sort of aesthetic or the same feeling as a recording, but it's kind of different every time we play it. etc. So we're talking about the future super collider. So I thought I would mention also our sort of future plans with this project. As I said before, everything was sort of, all these tools, all these classes were sort of made to respond to musical ideas. And now that I have a bit of a better overview of what we need and what would make sense for our workflow, I'm realizing that, yeah, there's some limitations. It's nice that we can divide the workflow a little bit, but I'm the only one working with supercollider, so a lot of it sort of falls on me to coordinate the others. And also our DMX situation is a little basic. So the next plan for us is to build. I started working on a timeline interface, sort of a DAW-ish looking thing that can accommodate these POO situations. The Kempers accept 14-bit MIDI, so that'd be nice to be able to send over there. And then also the processing stuff will be available. Torfinn, the other guitar player, has been working a lot in the last years as a light engineer. So now he's got a Grand MA set up, so we'll be interfacing with that as well. And hopefully with a bit of a graphic interface, we'll be able to collaborate a bit better and work in the same environment. Yeah, that's all for me. I kind of lost track of time here, but I don't know if there's time for questions or comments or yes.
So it seems like within the system you have set up right now, kind of really lends itself to like a kind of gent or like most gent aesthetic. So I'm wondering, in terms of, based on at least what I would show.
Sure. Yeah.
Like, is there any thought about like what the influence of using supercollider and some of the maybe generative elements in terms of expanding aesthetics beyond?
Yeah, so one thing I didn't show so much of is often we do a significant amount of improvising in our sets, and that usually goes in sort of a noisy direction, like noise. And that's usually me in supercollider go crazy. Also, because I have this tablet interface, I've been able to sort of design some instruments for the others to play as well. They're not comfortable with the code interface, but a tablet is a little bit more approachable. And then in those improvisations, they can also become a little bit, yeah, sort of a very different genre. But yeah, I think with this timeline approach, I'm curious. This is also a little bit inspired by Eric Slater's recent work with a timeline program in supercollider. And he can also do, for example, in his timeline, running routines or patterns. And that could be interesting to do sort of composed, scheduled real-time processing or synthesis as sort of, yeah, to augment the other sort of sound design elements that we have. Yeah.
Good question. Within rehearsals, are you using the tablet interface to cue individual songs, or do you using other?
Yeah, usually I'm running. I have a function to cue from one section to another section, and then there's a bunch of flags for like, do we want to run with lights or backing tracks, or whatever. So
you're typing in.
Usually, yeah.
Are you using something in stereo front of house? Are you mixing everything internally?
So I'm connected to a mix rack on stage. I think I send 12 or 16 channels. So all the backing tracks go to different. There's synths, stereo. There's another set of guitars, which is stereo, mono bass, and then I have like my supercollider outputs, which is stereo. I also send the clicks. Those are each mono. So yeah, using lots of channels, and would probably use more if we had them. Anything else? Whoops. Any other questions? Feel free to come up and talk to me at lunch or whatever if you want to talk metal. Thanks very much.
So, okay, let's make a start. Thank you so much to the organizers of the Supercollider Symposium, Ted Moore and Sam Pluta. And also thanks Tom Hall for the heads up of this event. So this presentation kind of relates to a summary of a tool that I've been, I would say, co-designing for a few years now. And so the idea is to give an overview and highlights on the history, code improvements, and artistic outcomes. I hear some voices in the background, but I keep going. And this is also a follow-up of a presentation done at NUTAM for the NUTAM Supercollider meetups on the April the 24th. Sorry, but organized by Mike McCormick. So it has been nice to see also your work, Mike. So I would like to start with a bit of a video, like a video showing how the tool works and how it sounds, or as an example. So let's see if the sound works, and I can talk aloud a bit. Yeah, so it's a quiet sound, so hopefully I can talk a bit on top. So the MIRLCa library, if you like, works as a customizable worldwide sampler because it can retrieve sounds from Freesound, the collective online database Freesound, which has more than 500,000 sounds under Creative Commons licenses. And so that, in a way, the kind of vision is that it can result in a low entry access suitable for music improvisation and live coding, because you work with samples. And so here you see a rehearsal for a performance that was delivered at the University of Nottingham in November 2023. And the idea here, well, is to, as you can see, is to kind of use a high-level language, and I'll tell what are the technologies behind that allow for this. But then you can work with the Freesound kind of descriptors, such as tags. You can query by tag, and then you have a sound out of it, and you can manipulate with easy functions, change the play rate, or like find similar sounds, apply some effects, and so on. So I'll keep going. So a bit of context and motivation for this library. So this started around 2016 when I was at Georgia Tech, and the idea was kind of to explore in kind of music information retrieval techniques applied to live coding, and what are possible ways to do that. And so in this paper published at the Computer Music Journal, together with Alexander Lerch and Jason Freeman, the idea here was to explore different approaches, and that included three main approaches. One was audio repurposing, which is what you just seen now, really like retrieving sounds from a sound collection based on MIR descriptors, but also we explore audio rewiring. So from an input signal, how can we then maybe transfer that to another type of sound or a complementary sound, and also audio remixing, which would be having several input sounds, and then how can we then make decisions on that. And the findings of this paper were that you can use rhythmic and tonal properties, which are kind of mid-level descriptors, together with text-based information, such as tags, to offer a close approach to a high-level features such as pitch and rhythm. And so then after like this initial work, one of the problems of using in particular the MIRLCa repurposing approach was that given like this huge large database of Freesound sounds, you may kind of have or retrieve sounds that you really don't want in particular contexts, or unwanted sounds or bad sounds, however you want to name it. So an example I like to give is, this was for real, so you are kind of in a context of a performance where you expect to retrieve sounds that are kind of noise sounds or glitchy sounds. It's kind of a festival of noise music, and then you retrieve a sound of a melodic riff guitar, which is kind of very out of the blue, and it's this kind of problem, I guess, motivated the development of MIRLCa. And thanks to the Human Data Interaction Network plus Grand Art Music Culture theme, led by Atao Tanaka, so the project received some funding to develop the next stage in a way, and whether we can use machine learning to filter those sounds that are unwanted for particular context. Still, both MIRLCa and MIRLCa kind of are embedded, and MIRLCa builds on top of MIRLCa, if you like, and both fulfill this vision of providing an easy to use and customizable worldwide sampler, but in this case, MIRLCa can give this customization. So how it works, this is a bit of a diagram that outlines what's behind the scenes, and it's worth mentioning it's a collaborative work, not only because of using crowdsourced sounds from Freesound, but also building upon existing tools, such as SuperCollider, of course, by James McCartney and others, but also the Freesound Quark by Gerard Roma, and that on top of Freesound API and Essentia, developed at MTG, at UPF, and also Flucoma, led by Pierre-Alexandre Tremblay, Owen Green, and Gerard Roma. Ted Moore also contributed. And so these tools are kind of behind, and thanks to those, MIRLCa and MIRLCa can exist. So just wanted to mention that, and you can see in a way, yeah, so MIRLCa is kind of on top, but speaks with the different libraries. And so, as mentioned, well, receiving this grant meant that we could organize some workshops. That was during especially COVID times. So they were online. That meant we had international reach, and we also were able to organize 3 concerts. But that was a way of pushing the tool forward, getting feedback from live coders, and also incorporating their feedback in the tool, seeing others, how they use the tool, how they adapt and customize, and observing, and kind of that was a bit, yeah, co-design techniques, I would say, because it was in conversation with the live coding community. And we did also impromptu performances, work in progress sessions, where the kind of participants, those who wanted from the workshops, explored the tool, share videos. And so, yeah, that was also interesting to see different uses. And then you can find an analysis under this article published on Organized Sound. And this is within the special issue Live Coding Sonic Creativities, co-edited with Gerard Roma and Thor Magnusson with the help of Lee Landy. And this special issue, just to highlight, contains 15 articles around live coding and sonic creativities. And this paper in particular, or article, talks on the qualitative approaches from the workshops, experiences, work in progress sessions, and performances about how live coders are using the tool. And here is an example of a work in progress by Hernani Villaseñor, who works very much on this blank canvas and start from scratch. So I'll also show a bit and talk aloud. I'm doing on time now, I stop this. So here, Hernani is starting from this white canvas. And a typical approach is starting with a random sound. Then this is kind of filtered with MIRLCa. So there is a model behind. You can train your own or use the one by default. And then it predicts the best sound from the model. So it's not, I mean, it's random, but it tries to provide a subset of favorite or more likely, so sounds that you will like more like, potentially more than without the tool. And then you can retrieve a similar sound of that random to kind of create a similar aesthetics, and then change the sample rate. And so we also presented at NIME, the conference New Interfaces for Musical Expression in 2021, the system architecture. So if you want to find out more, you're welcome to go there. But just to highlight, the approach here is to offer a live coding environment where the live coder can train their own models. And this is highly inspired by Rebecca Fibring's interactive machine learning approach to NIME with Wekinator. So yeah, just moving on. And then from the Organized Sound article, there are still, you know, even though the vision was, can we avoid like this musical guitar riff in a noise music concert or performance, there are still some hindrances. For example, you might still get sounds that you don't want, or unwanted sounds. Then also the training, even though you might train in an hour a model, but still it requires some time. And so that might, affect the immediacy of improvisation. And then the learning curve of all the different libraries might become steeper than before. So it's always, nothing is perfect, I guess. So always, but this also guides, what should be next, how to improve the tool. And more recently, we have published this paper together with Gerard Roma on the human-machine agencies in live coding for music performance. So in a way also from using the tool as a personal practice and Gerard using his tool, we just discussed and created this framework in a way to explore what are the agencies in live coding and to find out that it's not only the human live coder and the machine live coder, if you like, or the agent, virtual agent, but also there are other agents in a way, or aspects that have agency, including data, but also the software, the libraries, and so on. So that's a pointer to this paper. So it also highlight in terms of technical developments, the tool, like the funding stopped, but the tool keeps being developed, especially under artistic demands. And just for, the occasion of giving the talk here, so you can find now an updated version of the tool on GitHub. Still is not, like a supercollider Quark. It will eventually be someday, but things take time. But yeah, so here, feel free to explore it, but it contains the different libraries at the latest stage, the one that I'm using at the moment, but with many features to be incorporated. And so there is, compared to the previous release or publication, a bit more of organization with the code, so trying to divide the methods by performance, training, utils, and then what is more public, what is more private. So a bit of organization there. There is also, oops, I jump here, some supercollider help files so that they are embedded in the tool, and you can explore that too. In terms of the artistic outcomes, I would like to highlight a few. This Dirty Dialogues is a live album or live album that we recorded within the framework of the MIRLCa project under the HDI funding, the EPSRC HDI funding. And so that was also an improvisation fully. So we discussed what we wanted, but it was a full improvisation, and we audio recorded, video recorded, and it was also at the end of the COVID stages. So, well, just to say that was together with Dirty Electronics Ensemble, John O'Gara and myself. And you can see a bit of what it was. Another example, this is more like a solo performance using Hydra for the visuals developed by Olivia Jack, and that was, yeah, another type of concert using the same tool. And just to conclude, future developments, the idea is to improving the MIRLCa tool according to artistic needs. Also the forthcoming ICLC conference 25, International Conference of Live Coding, which will be held in Barcelona. We have a piece selected called Sensing the Alice Hall Forest. So we are building a data set of natural soundscapes, and then through the tool of MIRLCa areas to also explore any patterns, anomalies. Can this, maybe connect to climate change? So that's kind of under another project called Sensing the Forest, and that's the next piece that I'm working on. Then also improve the documentations, and as mentioned, the future, hopefully this tool can be a quark, a formal quark. And so, yeah, just to also comment, the tool follows, as you can tell, the slow research principles. It takes time in the end, but thanks to code sprints, hackathons, also, you get some work pushed forward. I want to thank the founders, the PSRC HDI network for allowing the tool to, move forward, and all the collaborators and supporters. Also, one of the pieces for boxes was funded by the MUSAI project, by the European ERC project led by Professor Georgina Born. I'm thankful to Live Coding community, Live Codera community, Super Collider community, Freesound community, Flucoma community, MUSAI community, and 9 communities for their direct or indirect help in the development of this tool. And thank you especially to Gerard Roma for constant mentoring and guidance in these different tools. And yeah, that's it. Thank you so much. Do you have any questions or comments or?
Yes, I was curious how you deal with latency. So in a live coding environment, are you always downloading your audio from Freesound in advance? Or if you're downloading it on the fly, what's your approach to dealing with latency, especially if you have an audio file of the financial side?
So
the bag in the box.
Thanks for that. Yeah. Thanks for the question. So the approach is very much inspired by, I guess, the 4 years at the Montfort University, the sound-based music approach that, maybe it's good not to be like everything under beat. So maybe it's good to have, sounds. Can you hear me?
Yeah, it's paper mentioned. Yeah.
The sounds have their own rhythm, and so embracing that latency as part of the aesthetics. So yeah, I guess that's not everybody's cup of tea, but that's kind of the approach of the tool. But as future kind of features would be nice also to have a bit more, I guess, more control on the rhythm. Right now it's quite free.
For as we find a table for now, we can set them up for here, and we can make one. I'll set one up and then.
Does this reply your question?
It's about very simple output. So else like another detailed structure and complicated one.
Sorry, can you rephrase that?
The MLP you're using is rather small. We try to use a bigger one.
Problems to be solved.
A bigger one?
Larger MLP architecture.
Oh, yes. So if a bigger data set, you mean, or a bigger?
I think the question was a bigger network.
A bigger?
Right.
Sorry, the sound is not very good.
Question is, have you tried using a bigger MLP, a larger
bigger
neural
MLP? Not at the minute, because yeah, I mean, after some trials and errors, this was kind of the one that has been working, and other fires came. But yeah, that's a good point to try a bigger one. So yeah, thanks for the suggestion too.
One more. is what tools are you using to interact with the cloud from SuperCollider?
What tools? FreeSound Quark, but the FreeSound Quark is kind of the language behind the scenes. That is kind of the client of the FreeSound API for SuperCollider. You can download it and try, and yeah, that communicates already via Essentia. The Essentia is kind of the analysis tool set that the music technology group developed, and that builds on Essentia. But yeah, that's what is kind of speaking with the FreeSound database. The idea with Milk is that it gives the more, I guess, the live coding vibe, so that you get these looping sounds, and then you create groups. So that's explain what what's added on the README file, but it gives like a bit more liveness, if you like.
The last question comes from the chat. Is it possible to use using Tacoma?
Is it possible to use? Sorry, it's cutting a bit.
Is it possible to use the tool without Glaucoma?
Without Flucoma, yes. Then you can use the, so back to the, hold on, the architecture. And some recorders prefer not to use it, by the way. So the Milk, you can use Milk rep without. So it is Saladino. For example, she has on the MIRLCa website a video of how she's using Milk without MIRLCa. Entitled cycles.
I mean, there's no cable. Oh no! Look at.
Thank you so much.
Good morning. And I would like to say thanks again to the organizers of this event. It's really exciting to see a SuperCollider Symposium happening again after many years. In the interest of time, I would like to just dive in. I will be talking about a code library, a Quark of mine called JITModular, which I use in the classroom and also for my own sound design. So what is JITModular? I call it a sound design library. As mentioned, I use it for teaching synthesis in the classroom as well. It is based on JITlib, the just-in-time library, which is so named because patches or connections between audio processors may be made just in time. In a way, it's a usage pattern, because there are some things you do with JITlib that you will not do with JITModular. There are other things you do with JITModular you don't do with JITlib. So let's talk a little bit about that difference. In normal JITlib usage, we focus attention on a node proxy, which I can think of as something like a channel in a DAW. So it has sound sources. It also has room for effect inserts in various types of processors. They can get fairly complicated. A key feature of JITlib that I take advantage of in JITModular is the fact that you can patch proxies together. One proxy can read another proxy's signal. This is extremely useful. So in JITModular, I refocus it a little bit. So I use a node proxy as a synthesis module. So in VCV rack, you would have a separate module for an oscillator, a separate module for a filter. The scope of the module is fairly small, so the kind of complication with a larger node proxy I'm trying to avoid. Then we collect several of these into a proxy space and use it all together as a monophonic synthesizer. A major reason for this is that I wanted students not to have to deal with really big code blocks. We can even start with, like, the first module I ask them to do is just a single line. This is fairly easy to explain, right? Then I also wanted to be able to save and restore patches in their original state. And there are some kind of slightly tricky issues about buffers and other resources that needed some attention. So I added those features into this library. So what I'd like to do is to introduce the basic usage by building a simple subtractive synthesizer with a sequencer. Step by step, should take about 5 or 6 minutes. Then there are a couple of other features I would like to touch on. Wrap up and have time for questions. Okay, apologize that I'm going fast, but time is really short. So in JITModular, the main object we're using is a JITMod patch. This is basically a wrapper around a proxy space that has some extra features in it. So if I go here, I already have that there, JITMod patch.new. This pops up a window which has some conveniences. It can display buffers. It can display MIDI controller mappings. Here, it will show you connections between modules. And this bottom part is a standard JITlib proxy mixer, which gives you access to each module's status and parameters. Over here in the IDE, we've opened up a code window that is associated with the patch. These are synced, so if I switch to this window, I am now outside the patch. If I switch back here, I am now inside the patch. So as I had said, modules are implemented as node proxies. And in a proxy space, the way you do this is you assign a function to an environment variable. Every patch, I felt it's really helpful to have a standard, like one place to put your hardware output. So every new patch creates an output module for you, and this is the only one that I will play. Everything else needs to be patched together and rooted into that. So here's what that module looks like. You have a function. I recommend using closed functions for savability. Function arguments become control inputs. And here is like, again, I really want to streamline things for the students. So I created this shortcut for an audio input into the module. Okay, let's make an oscillator. Now here, to save some time, I'm going to load up some prepared code, and you can see that the IDE is shifted. So oscillator equals this function with a frequency input and an LF try. Let's create it. And you'll see in the window that it has now been added to here. Patching. Basically, we take the source module, we throw it into the target module. It is possible to have audio inputs with different names, but if you just use the defaults and you have a single input, then it's very, very simple. So we can just OSC to out. There we go. One sticking point I had with students in years past is how many channels does the module have? And if you have mono versus stereo mismatches, that gets really tricky to explain. So I just make all of the audio modules stereo by default. Okay, if you wish to add another parameter that is not already known in the spec.specs library, you can add a spec for that. So I will actually do that to switch over to a pulse wave. Now let's add the pulse width. Let's add the pulse. So here's one of the key benefits. We changed the oscillator, but the connection stayed still. Okay, so those are the basic mechanics. You can define parameter ranges, you can define modules, you can connect modules, right? Pretty much everything else works the same way. So for example, I can put that back on, add a filter, patch in the filter. So we just say oscillator. We say oscillator to filter to output. And this is pretty straightforward, right? We can do the same thing with an envelope generator. And now we have some degree of note control, right? We can open the gate, close the gate. One detail about envelope generators is that the word gate is reserved for JITlib. We can't use that for our own purposes, so I just settled on a standard of GT. Also, we want modules not to die, so don't use done action 2. At this point, you'll want to trigger the envelopes. One way is that if you access the current patch and init MIDI, you can then use a MIDI keyboard to play it. I don't have time to demonstrate controller mapping, but that is also an option. You can learn control. Say, I want to learn the filter frequency control with a frequency control spec, and then turn the knob on your controller, and it will be associated, right? sequencing can be done with a new proxy role, PS set for proxy space set, which will set parameters in the proxy space. So if I set a tempo, let's set a quant, and let's run it. Okay, and then, you know, as you can have students, mess around with the controls and have fun. So there, in just a few minutes, is a simple subtractive synthesizer with a sequencer. Okay, a couple of other features to talk about: patch saving and loading, buffers, open sound control, and then there's one other surprise at the end. If you just save the document, you will have the code, but you don't know which are the last bits of code that you ran. You don't necessarily know what the current state is. So for that reason, there are save and load buttons in the GUI window, which will preserve the entire state of the patch. I did find that some really complex patches may have some trouble loading. Since the intended use is for teaching or for some smaller scale experimentation, I haven't found that to be a big problem, but just don't expect too much. This is really important in the classroom for students to submit their homework. Okay, buffers. Kind of common question that comes up in the forum sometimes is, when I'm in a proxy space, right, every environment variable has to be a proxy, so what do we do with buffers? And for JITlib, there are various workarounds. In JITModular, I could implement features, so I made it so that you add the buffers into the patch. Let's take a look at that. So I can load an example. Okay, familiar sound. Let's mute that though. So here's what I mean about loading. To reproduce this patch, it had to load the buffer, load the modules, recreate the connections, right? And so it's no problem. But here it shows you how to add a buffer in. So we access the current patch. We add a buffer. We give it a name. It has to have a name to access. And then this alternate buffer class is actually the one that handles the display in the graphical window, but otherwise it works just the same. Then in the module, we use the name as a proxy. So I just decided to put the buffer number into the patch as a single value node proxy. One advantage of that is that you can swap out buffers and it just changes the buffer number here and you get immediate results. So if I replace this buffer, okay, and it automatically updates, and then I could resave and it would change the saved buffer. Buffers are saved into a folder alongside the patch file. So there is duplication of audio data, but for me it's worth it to have reliable save and load, right? I won't say too much about open sound control, except that it's implemented by mapping OSC paths onto MIDI controller numbers and then just leveraging the existing MIDI methodology. You can add this into a patch by accessing the current patch and then doing a MIDI OSC bridge method. You define a profile that makes these associations, right? Related to saving and loading, there are custom init and cleanup hooks. This MIDI OSC bridge is a main use case for that. So I would say like this actually is the correct way to write that, because if you write it as a custom init function, it will restore the next time you open the patch. Okay, and now for a bit of fun, right? If you want to use a JITModular sound as a synth def, for a long time, the only way to do that was completely by hand. It's a bit experimental feature, but there is a synth def button where if I click that, now it's created a new document in the IDE, and it's attempted to write in all the elements of the patch. Now, I can't promise that it will handle absolutely everything correctly, so if you find bugs with it, feel free to report them and I'll try to deal with them. But at least in this simple case, you see there's a control input for the buffer number, there's a control input for the amplitude. And this will actually play. I did test it. I won't do it right now because I'm almost out of time. But that's kind of, it's, you know, the way that it writes the synth-dev is not really people-friendly, but if you just want a quick and dirty conversion, you can try it. I'm kind of proud of that, actually. Okay, so, and I guess in conclusion, I will just say that that I still use this for my own sound design because it's a really nice way to save and restore experiments. You know, mess around, play around. It's a lot of fun. The one drawback that I should mention with it is that JITlib doesn't really manage node ordering when you're using audio rate controls. That could introduce block delays sometimes. I haven't found that to be a big problem except for FM with feedback. Because, you know, FM, if you have a block delay, then the phases can get messed up a little bit. So, you know, but I just accept it for this purpose. In the classroom, I find that at least where I teach, students really do not get along with code. So I find that this library makes the difference between like zero engagement versus some engagement. So I think in that sense, it's been worth it to put this together. So I think that's all. So if there are any questions, I'm on the Zoom call and we'll be happy to try to address them. Thank you. Okay, so any questions? I can't hear clearly at all, so.
The question is, how are you doing the saving? Is it an object on archive or something else?
Oh, no. It's a custom kind of format. I can actually show show an example. Let me see, share sound.
This next one might be one. It's one more tall.
Yeah, let me actually open one of those. Just a second. Where am I? I've got all this other stuff on it. Okay. Let's pick one of these. Let's do the yeah, so what you get is this kind of an initializer for the proxy space. There's actually the entire document contents without modifying them. Yeah, and then we go into the proxy space and it will just and a lot of the code to generate this output is kind of cribbed directly from JITlib, but I had to adjust some things to get all of the connections, the parameters right. So the loader will just run this and it will pass all of these objects back.
Hi everyone. Thank you so much for organizing this and for enabling us to join remotely. It's been a pleasure to just see everything from home. Yeah, when I proposed this, I wrote down the title for the talk, which is supercollider-gst-rtp, which I know makes no sense. So I rethought of it, and it's more than just about the plugin. It's about like these strategies that I've been playing with since 2019 on how to stream audio to multiple clients, especially clients running a web browser, mostly because I wanted to do performances and installations that use the audience smartphones. A bit of why the first thing actually is not there is that I really wanted to play around with multi-channel setups and I had no access to them. And once I went to a very fancy place here in Berlin, and I got very frustrated that I would not have access to multiple speakers like that. So I thought, okay, the easiest thing is smartphones. So I started really in 2018 finding out ways to do that. So the first thing was that was the main motivation. And funny, and I did the first thing in 2019 and then came COVID. So all this work that I put into finding out ways to do remote setups was very handy during the COVID. The other things that interested me at the time was strategies for changing the specialization methods algorithmically, depending on the number of channels that you have. So what happens if you just suddenly have one channel less or one more? What can you do? And SuperCollider is great for that with JITlib. Then also because of COVID, during COVID, we did a few web installations. And because I could use web audio, but I was so already, not only me, but the people I was working with, we were all used to do SuperCollider. So one easy solution was to run SuperCollider on the server, on the web server, and then stream audio. So that was also one of the starting points. And lately, because of all this work, it showed that now it's much more flexible and easy to do this kind of remote collaborations. So I will show a few of these things that I've been doing and then introduce this framework. So the first things that I tried in the beginning was both Ninjam and Sonobus, and also IceCast. So IceCast was great for if you have SuperCollider running on a web server, you can stream that to a HTML page, and then people can listen to it. But it has a lot of latency. It is not good if you want to do collaborative playing. It is pretty good if you have a stereo stream and you just want to like a web radio or something. So we did 2 installations with that in the University of the Arts in Berlin, where I studied at the time and where I work with Alberto de Campo. And for that, it was pretty okay, but still, I really, for performances and also installations that are interactive, I really wanted low latency. So I tried these other things, Ninjam and Sonobus. Sonobus is pretty good for collaboration, but still you need to do all this setup with routing audio from SuperCollider to another to have a client running, and then you have to have a Sonobus server, and to listen to it, you can't stream it to the browser, so you need also Sonobus client on the other end, so not ideal. In 2019, I wrote the software that I called Spotify. It was kind of a joke at the time with Spotify and specialization. And I wrote it in Python, and it uses Jack. So it creates multiple Jack clients according to how many connections you get from WebRTC. So this Python software is handling all the WebRTC part, encodes the stream from Jack and streams it over. It can dynamically allocate new clients and notifies any registered OSC clients of new channels and so on. It worked well for one installation I did, but it showed that after I had 10 clients, it started to glitch because of the performance in Python. So it was not the ideal solution. But it powered this installation that, because of COVID, it didn't have so many visitors at the time. So I had a maximum of 10 people in the room. So that worked pretty well. The installation was composed and built on SuperCollider, but it had a pretty structured narrative of 13 minutes that kept looping, but everything was generative. So all these loops changed over time, and it also changed all the sound processes that were running. They changed accordingly to how many clients were connected, using JITlib elastic reshaping. That was a really, really nice thing, so that it would reevaluate all the NDEFs, and then check how many clients it has in that moment. and then spatialize accordingly. The second solution that I came up was using YAWN's WebRTC gateway with this streaming plugin, which it opens a RTP port on the server, and you can string one channel to that, and then it will broadcast via WebRTC to clients that are connected with the browser. It is very efficient, has a very good performance. On Linux, you could just open a Jack client with GStreamer and then stream it over RTP to YAWN, and then YAWN handles all the WebRTC part. That you can create via the API of YAWN. You can create dynamically also those streams. So it was pretty much like the Spotify solution, but way more robust. The problem was the setup was super complicated. In my machine, I would have to have scripts that keep reading if there are new clients, create a Jack clients for that, create the GStreamer pipeline, and then connect everything and send, and then connect also to the supercollider output. So I would have to start supercollider with as many outputs I wanted, and then do all these Jack connections. This was a pain to keep. For every performance, I would have to do that, or for every new setup. But at the same time, it worked very well for my projects. So I did build this whole live coding setup, so-called CoLive, that multiple users. It was running on a web browser. There was supercollider running on a web server, and people would join and program or live code together. So everyone has access to the same canvas, which is a nonlinear text editor. This graph is sort of the infrastructure of that. It sort of tries to be distributed, so you can run multiple instances of CoLive, and they try to sync the state with each other. You have YAWN's WebRTC here and supercollider streaming with Jack and GStreamer, as I just explained. On the client side, you have the browser and WebRTC stream. This thing, as I said, was way too complicated to set up. I always had to fix some Jack connections and things like that. Had some scripts that kept as watchdogs. So I kept thinking I wanted a solution that was not depending on anything else apart from supercollider to do the streaming. Then I can have a server or something that is stable and has the channels there for me, and I just need to use some UGents. So I wrote this plugin called the supercollider-gst-rtp, which implements the pipeline that I was using on GStreamer, but it implements as a plugin for supercollider. So the way that you use it is just you first register with a symbol your output, let's say an IP address and a port and the server. And then you can simply call GST-RTP out that symbol so that it knows what out you're talking about, and you send the signal through that. Here is just an example of how you can send it to yourself. The in symbol can be is not the same as the out symbol, so you can have the same names for in and out, but they're not related at all. It's just a matter of how you use it when you receive it or you send it. This opens up a lot of possibilities because you can use all the supercollider infrastructure to do routing and buses and so on, and then listen to a bus and route that into RTP, or this becomes very, very flexible. And thanks to this flexibility, I changed how CoLive works. So before it was one stereo string to every client, and then now I was able to do different setups according to performances or also to clients. So nowadays, for example, if it's a desktop connected, like a web browser on a desktop connected to CoLive, it will get the stereo mix. But if it's a mobile phone, it will get a sort of a granulator effect that is with individual channels for each phone. So in a room with 50 phones, I put this video for this performance where we had, I think, 65 or 70 phones playing. And I can dynamically mix between sending the stereo mix to all of them or just the granulator and everything without having to handle jack connections or anything. Is everything from supercollider. I will play. I'll try to play this. Let's see if it will work. Yeah, you can now hear it's only the phones in the room. Okay. Another thing that opened up with this using this kind of setup was doing this collaboration with the artist Roberta Bussician, where we had Raspberry Pis with USB microphones and battery-powered Raspberry Pis, and then using smartphones as hotspots, so people could do streaming of field recordings. So she distributed this around the world. She sent to some people some Raspberry Pis already with the setup. And once they turned that on, if the Roberta would go to this remote listening.space URL, and they appear as strips on this mixer. And then using web audio, you can have some EQ and send effects and some basic mixing. And you can record that setup, that session on the client side. So multiple clients have different perspectives on that field, on that distributed field recording performance. And Roberta would do those performances in spaces like in real life. So yeah, so that was also powered by GST-RTP. And the final case, big case, which is microwebs, which is a project I started building up on top of GST-RTP. Basically, the idea was how I can make distributed synthesis, let's say, with these dynamic ideas of recompiling the sound processes or when I have new clients and so on. But then as well, I wanted to use only the phones of people as output this time, not mix with a PA or something. So I came up with a whole framework for that, thinking of the idea of distributed sounds. And in this case, everybody on the same space, let's say. And this is the kind of interface that you see on the phone, and people can also influence the sound, but sometimes I perform with that and sometimes without influence, just streaming the sound, and I control it over with this interface. And this was all that was needed to do this routing, which is, for me, was a really, really magical, and I didn't need to handle anymore the whole jack situation. There is a special performance I did with this because of the festival I went to play in Norway got canceled, and then we had to play without infrastructure in a mountain. There was no speakers or anything, so the only possibility was to use this kind of setup, and was very, very magical.
What, you're gonna take it now? No, the lid. You see the lid, the white one? Oh no, okay, you need that. No, it doesn't matter. So we start to kind of like this take what's out here. So that means that, and you take it out and then let it dry, and then you just put it back in the lid. It needs to get hard enough so that it's clean.
So in that case, all the sounds I'm playing with this interface, but everything is that you're hearing is coming from people's phones around the microphone there. Some other use cases for this is 2-3 weeks ago, I was supposed to play with Alberto in a gallery space, and because my dog was sick, I couldn't go. So I quickly sketched a thing that I could send my Super Collider output into a web page, and I asked Alberto to do the same. So I opened his page and he opened mine. We routed each other's through Super Collider. So we both had our own mix of the whole thing. So he could control and mix my sound in the gallery, and I could also on my side listen to him, and then we just played together. And I made also quickly a web page where people could see who was playing in certain moments. So this is how it looked. in this case, I was sitting at home and Alberto was in the venue, which was just the ability to do that very quick in a few hours was great. So, some other use cases that you can do is you can stream directly from SuperCollider to another SuperCollider if you have the IP, and that is very, very easy to do. This is an example that I've played also, where we can come up with a protocol, so who listens to what port, and then we just stream it. Also, you can do broadcast streaming, so you can broadcast, and then whoever wants to listen to that can listen to. And this would be sort of a feedback matrix over the network using GST-RTP. Just as a quick example of things that you can do. And of course, you get some jitter in the latency, so that is also great for feedback. There are a few things I would like to do. So the bitrate for now is hard-coded. It would be easy to implement it is as a configuration, or an option, but I didn't have the use for that yet. I would like to receive WebRTC directly from inside of GST-RTP or GST-RTC, but I think this probably is supported by Stacker. I didn't have time to look properly at Dennis' project, and he will present it. So I'm curious because maybe Stacker can fully substitute it. So let's see what comes up. And that's it. Thank you so much. If you have questions, I'm happy to hear. So if anyone asked any question, I couldn't hear. Sorry, I didn't hear anything. I just heard a tiny noise.
Question is about the microwebs project. Were the phones interacting with each other?
In that case that I showed, no. I have the plan that's one of the reasons I would like, for example, to get WebRTC audio back into the system and send back, so you could do some sort of feedback over the network with the phone's input. In the current state of it, people can influence using gyroscope and or the sliders there. There are a few things that they can influence the controls of the sounds. Yeah.
Other questions?
Question about sample rate. I think it was mentioned it's hard coded. That's why I'm just curious if it's hard coded to a certain browser or that the server runs a certain rate. And then the kind of question, is there a like sampling involved in the network system?
Can someone say that on the microphone, because it's very hard to listen?
So the first question is, you said that the bitrate was hard-coded. Does the servers need to run at a particular sample rate because of that?
No. That is happening on the GStreamer thread. So server is sending audio to GStreamer, whatever audio, and GStreamer is encoding that. So did it matter that it's in the plugin there's a hard-coded bitrate, but you can also change it at compile time and run it on another bitrate. But the server has nothing to do with that.
So is there resampling happening to make that happen?
Well, there is not from the server side, but on the GStreamer side, there is during the encoding for Opus. So yeah.
No, I think that's it. Thank you.
Other questions?
Thanks. Right.
If you could repeat it, please.
Question is, how are you handling connections over the network or over the internet if you're not on a local area network?
So most of all of the broadcasting over WebRTC is done by Janus. So I have a server that is running this Janus WebRTC gateway, and this one is the one that opens the RTP port. So I just send this to Janus, and Janus has multiple ports that are available. So the web browsers, they connect to that. And then using this other software called TCP/OSC router that I also wrote, Janus via WebSockets, they tells me, or tells SuperCollider that a new channel is showed up, and SuperCollider can create its own GST RTP dynamically and send it to Janus, and then that goes into the web browser.